Thanks for watching, and today I would like to tell you what happens if you diagonalize a matrix and you get complex eigenvalues. And in general, it's just a pain to do, but at least for the 2 by 2 case, it's still hard, but not too bad. So let's take this matrix, the following matrix. So A is 1, 5, minus 2, 3. And well, let's first find the eigenvalues. So let's do determinant of lambda I minus A. So that's determinant of lambda minus 1, minus 5, 2, lambda minus 3. And then that is lambda minus 1 times lambda minus 3 plus 10. So expand that out. So lambda squared minus 4 lambda plus 3 plus 10. And that's lambda squared minus 4 lambda plus 13. And you want to set this equal to 0. Well, usually you're lucky that you can factor this out. Here, unless you're really good at it, it's hard to factor out because indeed there are complex eigenvalues. And for this, let's just use a quadratic formula. So minus b, so 4 plus or minus square root of b squared, so 16 minus 4 times 13 over 2. And that's, so turns out you do 4 plus or minus square root of, I believe, minus 36 over 2, which is 4 plus or minus 6i over 2, which is 2 plus or minus 3i. So, couple things to notice. First of all, well, there are complex eigenvalues. Some people, like my linear algebra professor, says it's not diagonalizable. I'm still salty about this because I think it's still diagonalizable, but it's just a matter of convention. Okay, it's okay. I think I survived. First remark, the eigenvalues are complex. Second of all, notice they always come in pairs. And in fact, it is true that if lambda is an eigenvalue, then so is lambda bar if A is a real matrix, because you can always take AV is lambda V, put bars everywhere, then A bar V bar is lambda bar V bar, bar, and well, A is a real matrix, so you just get A bar is A. So you get A V bar equals to lambda bar V bar. So lambda bar is an eigenvalue, and we'll see in a second V bar will be an eigenvector. So it's normal that they come in pairs, but the nice thing is in practice you just need to worry about one of them. So let's do lambda equals 2 plus 3i. Well, that is the null space of 2 plus 3i I minus A. And that's the null space of, so in this case, you let lambda be 2 plus 3i. So you subtract 1 from lambda here and 3 from lambda here. And you get null space of 1 plus 3i minus 5, 2, and minus 1 plus 3i. Just to make things nicer, we can interchange the rows, and it's the null space of 2 minus 1 plus 3i, and 1 plus 3i, and minus 5. Okay, and there are two ways of doing this. You could either divide by 1 plus 3i. So let me show you the slow way. The slow way is to divide this by 1 plus 3i, and you get, it's the null space of 1 and then minus 1 plus 3i and 2. So here you divide by 2, and here you divide by 1 plus 3i. So 1 and then minus 5 over 1 plus 3i. The slow way is, well, we don't like i's on the denominator. Let's just multiply by the conjugate form. So let's do minus 5 over 1 plus 3i times 1 minus 3i over 1 minus 3i. And we get the numerator is minus 5 plus 15i. The denominator is a squared minus b squared, which is 1, minus 3i squared, which is minus 9, so 1 plus 9, which gives you, indeed, minus 5 plus 15i over 10, and that is exactly the same as minus 1 plus 3i over 2. So the slow way is just doing, well, dividing by this number and then seeing that it's indeed the same. So it is indeed the same. Minus 1 plus 3i over 2. Here is now the clever way, but careful, you have to be sure that your answer is correct. And this only works for 2 by 2 matrices. So for 3 by 3 it's kind of harder, but look. We know that there is an eigenvector because we know an eigenvalue is 2 plus 3i. So this matrix cannot be invertible, okay? Because if it's invertible, it's not an eigenvector. Well, in particular, if it's invertible, you know that there is a row of zeros. So the first row should be 2 minus 1 plus 3i. The second row should be 0, 0. And that actually works for any eigenvalue, provided you're sure your answer is correct, and provided that you have a 2 by 2 matrix. For 3 by 3, it's a bit more complicated because you won't really know which row to eliminate. But here it's okay. And then, well, you find a null space of this, which just means you solve 2x plus minus 1 plus 3iy equals 0. And basically, if you do the calculation, you should get that it's the span of, so I think it's 1 minus 3i and 2. Because notice, if you actually do 2 times 1 minus 3i plus minus 1 plus 3i times 2, you get 0. So that's also a clever way of doing this. Or if you want, you can just put minus 1 plus 3i and minus 2 here. If not, you just solve for your equation. You basically solve, x, if you want, is minus 1 plus 3i over 2. Sorry, x is 1 minus 3i over 2, and y. And then you just do your usual null space trick. Okay, so that's the nice thing. We found an eigenvalue, 2 plus 3i, and an eigenvector, and it was very difficult. Okay, so in practice it's a pain to do, but here's the nice thing. You don't need to repeat this process for the other eigenvalue, because there's this nice fact, which I've sort of indicated here. If v is an eigenvector for lambda, then v bar is an eigenvector for lambda bar. So, an eigenvector for 2 minus 3i would just be 1 plus 3i and 2. So it's really neat. So nice fact. And as I said, they will always come in pairs. So even for 4 by 4 matrices, sometimes 3 by 3 matrices, that works. So fact. Okay. Lambda bar, which is 2 minus 3i, is an eigenvalue. And v bar, which is, in this case, 1 plus 3i, 2, is an eigenvector. And so if people ask you, find P and D, such that A is PD, P inverse, then D, as usual, will be the matrix of eigenvalues, which is 2 plus 3i, 0, 2 minus 3i, and P is your matrix of eigenvectors. So 1 minus 3i, 2, and 1 plus 3i, 2. All right, that's one way, okay? Now, the question is, what if you want real matrices? Because one thing that should have bothered you is you started out with this real matrix A, which I would like to remind you was 1, 5 minus 2, 3. Well, it's weird to write them as products of complex matrices. But it turns out there is a way to actually get real matrices for this. And the nice thing is you don't even need this second eigenvalue. So, let's go back to this. And it turns out this is a very, how can I say it? It's related to a very neat concept. It's in fact related to polar coordinates. So we'll be able to do matrix polar coordinates, which is really neat. So just stick around. So what if you want real matrices? Well, remember, one eigenvalue is 2 plus 3i, and the corresponding eigenvector is 1 minus 3i and 2. And notice lambda, we can split it up into real and imaginary parts. And also v, we can split it up into real and imaginary parts. Because it's 1, 2 plus I times minus 3, 0. And it turns out, if you let C, so if this is A and B, and C is the matrix AB minus BA, we should remind you a bit of a rotation matrix. So in this case, it's 2, 3 minus 3, 2. So the point is, here you put your real values, A and B, and then here you just do minus BA, and you let P to be the matrix of this one eigenvector, but with real imaginary parts. 1, 2, minus 3, 0. Then it turns out that A is actually equal to PC P inverse. So your matrix A, which was 1, 5 minus 2, 3, is actually equal to 1, 2 minus 3, 0, 2, 3 minus 3, 2, and 1 minus 3, 2, 0 inverse. How cool is that? So you do get A is a product of 3 matrices, and you might say, well, that's not very interesting. Ideally, we would like the middle matrix to be diagonal. Well, even though it's not diagonal, it's still super interesting. And let me tell you how it's related. So notice, take this matrix 2, 3, minus 3, 2. And what you would like to do is, just like in polar coordinates, we had r e to the I theta, take out the length of this vector 2, 3. Now the length is square root of 2 squared plus 3 squared, which here, I'm sorry, it's a bit ugly, but it's square root of 13. So it really becomes, if you think about it, the product of 2 matrices, namely, I don't know, today the light is very short. So it's square root of 13, 0, 0, square root of 13, and 2 over square root of 13, 3 over square root of 13, minus 3 over square root of 13, and 2 over square root of 13. Because notice, indeed, you can just multiply this row by square root of 13 to get 2 and 3, and this row by square root of 13 to get minus 3, 2. Why is that interesting? And I get to that in a second. So notice, I don't know if you remember this pattern, but A is square root of 13, 0, 0, square root of 13. And this should remind you a lot about cosine. Because notice, if you take the length of this vector, because we took out the length of this is 1. So really, this point, 2 over square root of 13 and 3 over square root of 13 is actually a point on the unit circle. So you can actually write it in terms of cosine theta, sine theta. And indeed, it is equal to cosine theta, sine theta, minus sine theta, cosine theta. Where what is theta? Well, in this case, it's just arc cosine of 2 over square root of 13. So what is this matrix? It's really what it is. It's a composition of this matrix, which is just scaling. So it takes a vector and scales it by square root of 13. And let's write it as S, like scaling. And this, I don't know if you remember, but this is a rotation matrix. So A is actually a composition of a rotation matrix times a scaling matrix. And that should remind you a lot of r e to the I theta. Because that's also what r e to the I theta does in the complex plane. It rotates a complex number by theta, and it scales it by this factor of r. So indeed, it shouldn't come as a surprise. This is what's called the polar decomposition of a matrix. Decomposition of a matrix. And how is it related to a diagonal matrix? Well, a diagonal matrix, technically, say 2, 0, 0, 3, is just a scaling matrix. It scales the first factor by 2 and the second factor by 3. And think about it as like no rotation. So it's like r e to the 0. Right? But here it's slightly more general. It's r e to the I theta. And just a little remark about the polar decomposition. So it's actually part of a more general feature. So this actually also works, I think, in infinite dimensional spaces and stuff. But polar decomposition, in general, what you do, you write A. So one thing though, here we have a multiple of the identity, so it actually commutes. So it's the same thing as SR. Okay. So you can write A equals to SR, where RS. So think rotation times scaling, where what are the requirements? R is called a unitary matrix. I think it just means that R transpose R is the identity, and S is just a positive definite matrix. So positive definite here just means its eigenvalues are positive. So indeed, that's what we did, but with the 2 by 2 case. But in general, I forgot what assumptions, but I think maybe any assumption, you can write A as a composition of a unitary matrix and a positive definite matrix. And how do you find this how do you find this S, the scaling matrix? Well, it turns out there's a nice formula. And in fact, in this case, if you calculate A star A, so, in this case, A was, remember, the matrix 2, 3, minus 3, 2. If you calculate A star just means a transpose, but if it's complex, you put like conjugate stuff on it. Here it's real, so it's 2 minus 3, 3, 2, times 2, 3, minus 3, 2. If you actually do this, you get something very nice out of it. So 4 plus 9, which is 14, 0, 0, 14. So not 14, 13. How did we get this square root of 13? Or literally, here you have a diagonal matrix. In general, it might look something else. But what you would do, you would take the square root of A star A. So in this case, square root of A star A is square root of 13, 0, 0, square root of 13. And that should give you usually your scaling matrix. So it turns out, even more generally, the scaling matrix is given by square root of A star A. Why does that make sense? A star A, it's a symmetric positive definite matrix, so it actually has a square root, and I made another video on that if you're interested. And then, so S is A squared of A star A, and well, how can you get R? Well, simply by just taking the inverse. So S is positive definite, hence invertible, because no eigenvalues are 0. And from A equals to RS, you just get R equals to AS inverse. And indeed, that's what you get. If you do S inverse, it's 1 over square root of 13 and 1 over square root of 13. And if you multiply this by A, you indeed get this matrix. But the question is then, is it unitary? And that's another very difficult question. But I just want to say it is true in general, and it's kind of nice. All right, I hope you like this complex extravaganza. If you want to see more math, please make sure and subscribe to my channel. Thank you very much.